Okay, so here we have your very basic parabola that has the equation f of x is equal to x squared. In the vertex form, and we'll look at why this is like this later, we have 1 times x squared plus 0. And right now our a value, which is the coefficient of the x squared term, is set to 1. And so this is what our parabola looks like. So if we drag the vertex, let's say we drag it 1 unit to the right, you can see that our vertex form now has the equation 1 times x minus 1 squared plus 0. So what that means is that we took our original parabola, f of x equals x squared, we dragged it 1 unit to the right, and we pushed it up 0 units. And so its vertex is now at the point x is equal to 1, y is equal to 0. So here's our vertex at 1, 0. And in our standard form, we have x squared minus 2x plus 1, because that's what we get when we expand this x minus 1 squared. Notice, by the way, that this is also a perfect square trinomial. Okay, when we drag it over another unit to the right, we now have x minus 2 squared, and again, still plus 0. And we have now x squared minus 4x plus 4. Again, a perfect square trinomial. Another perfect square trinomial at x squared minus 6x plus 9. So now notice as we go up. So now our vertex form, we have plus 1, and our vertex is now at the point 3, 1. Notice now that we are no longer a perfect square trinomial. We went up on the constant term here, so we have x squared minus 6x plus 10. We keep going up. Every time we go up 1, these numbers both increase by 1. So the vertex form, again, tells us exactly the location of the vertex. It's going to be x minus 3, so whatever sets that equal to 0 will be the x value of our vertex, and then plus 3, so whatever this value is here tells us the y value of our vertex. Okay, and meanwhile we've been keeping a the same all along. Well, if we now decide we want to change the value of a, notice that what's happening is that our vertex is not changing position at all, but the shape of the parabola is changing. As a increases, what we're doing is we are stretching our parabola vertically, which means that it appears to grow narrower. And as we get below 1, we would be taking our and compressing vertically, which makes it appear to be wider. Once a reaches 0, what we have is just a straight line, because we have f of x is equal to 0 times x minus 3 squared. And so all that's left is this value right here, and we just get the line y is equal to 3. And when a is negative, our vertex opens downward, and we get something that looks like this. Okay, so a will determine a couple things. It will determine whether the parabola opens up or down. Negative value of a means it opens down. Positive value of a means it opens up. It'll also determine the shape of our parabola, but it will not have any impact on the vertex, and that has only to do with where we move this thing. And so in the vertex form, our value of a, as that changes, it has no impact on the x minus 2 or the plus 2. On the other hand, in our standard form, every time we change a, everything changes, just because of the way when we multiply out the vertex form to get the standard form, then the 0.5 is going to get everything else involved. Okay, so let's look at a couple other features here. So we want to look at our y-intercept, and right now for this parabola it said 0, 4. And when we look at the standard form, we can see that very easily that when x is 0, as it is the case along the y-axis, our x values go to 0, and so that means both of these terms, the x squared and the x term, have values of 0. So all that's left is this 4 here. So this value here, which is in the ax squared plus bx plus c format, this is just c, and that's going to be equal to the y value of our y-intercept. To figure out the y-intercept from the intercept form, we would need to do the following. We would replace x with 0. That would give us 0 minus 2 squared, which would be 4. multiplied by 0.5, which would be 2, and add 2, and that gives us our 0, 4 y-intercept as well. Now, when we're thinking about plotting this, we want to think about a couple things. So the axis of symmetry is the vertical line that passes through the vertex. So as our vertex moves, our axis of symmetry will move. And what this means, this axis of symmetry, is that the portion of the parabola that's to the left of the axis of symmetry and the portion that's to the right are mirror images of each other. And so if we wanted to know, for example, this point right here, which is the mirror image of the y-intercept across the axis of symmetry, we know that it's going to have the same y value as our y-intercept, and we know that it's going to be the same distance from the axis of symmetry. So if it's 2 units to get from our axis of symmetry to our y-intercept, it's going to be 2 units in the other direction to get to that point that's the reflection. So that gives us this reflected point 4, 3. So if we were trying to graph this, we would now have both the y-intercept and this reflected point, which again we can figure out using the axis of symmetry. So just to go back a moment, when we have the standard form, finding the vertex is a little trickier than when we just have the vertex form. But fortunately, one thing we can do is calculate the x value of the vertex by taking the b value, which is the coefficient of the x term, and we would take the negative of that and divide it by 2 times the a term. That would give us negative 2 over, negative of negative 2, which would be positive 2, over 2 times 0.5, which would give us an x value of the vertex of 2, which is what we have here. Then to figure out the y value, we would just plug our value of 2 into this equation here, and that would give us 0.5 times 2 squared minus 2x, or minus 2 times 2 in this case, plus 3, which would give us a value of 1 for our y term. Okay, so that gives us a way to find the vertex, which we can do easily from the vertex form and with a little more work from the standard form. Okay, so we talked about the y-intercept and the y-intercept reflected across the axis of symmetry. Okay, let's talk now about the roots. And by that we mean, what are the values of x that will make either of these equations true when we set f of x equal to 0? The other way of thinking about it is that it's just going to be the x values of where this parabola crosses the x-axis. So let's take a look at those. Okay, so right here we can see we have it crossing at 0.59 and at 3.41. Now the way that we have for calculating this is the quadratic formula, where we have negative b over 2a plus or minus the square root of b squared minus 4 times a times c. And when we evaluate that, we end up with 2 plus or minus the square root of 2 over 1, or just the square root of 2, is equal to 2 plus or minus 1.41. So again, think about the fact that this term right here, which is the negative b over 2a, that has to be equal to the x value of the vertex. Because what we're doing is we're saying we're then taking the x value of the vertex, which is 2, and we're adding, in this case, 1.41 to get to one root, and we're subtracting 1.41 to get to the other root. So this gives us both of our roots, 2 plus 1.41 and 2 minus 1.41. So one of the things you'll notice is that as we move this thing around, obviously the values of our intercepts are going to change, of our x-intercepts. When the vertex is right on the x-axis here, notice that the b squared minus 4ac part of our expression here becomes equal to 0. And so we end up with just the x value of our vertex plus 0 and the x value of our vertex minus 0 to get our 2 roots, but these 2 roots then turn out to be the same point and at the same point, and so we end up with just the one solution to the equation, which is x is equal to 2. So that's this case when we have the vertex right on the x-axis. When the vertex is above the x-axis and the parabola is opening upward, it never crosses the x-axis. So what that means is that there are no solutions to the equation 0 equals 0.5x squared minus 2x plus 3. And we can see that because this thing never crosses the x-axis. What happens is we end up with a negative value in our discriminant. And our discriminant is just what's under the square root here. So when that is negative, we no longer have a real solution to this. So we get a question mark here in GeoGebra because it doesn't quite know what to do with trying to take the square root of a negative number. And we see that we have what are called imaginary roots, and we'll get into that more later in the term. So we would also get this situation if our parabola opened downward and we ended up with a vertex that was below the x-axis. So again, that would give us imaginary roots because again, we would have a negative value in the discriminant here, or in other words, a negative value under the radical in the quadratic formula. Okay, so that's the basic lay of the land for these items right here. In another video, I will talk about what we do to find the directrix and the focus point.